All right, I'm going to start 1 minute early so that all the presenters get their full 15 minutes. I'm Martin Maas, a research scientist in Google DeepMind, and I'm going to be moderating the memory allocation and management session 5C. So our first talk is by Nick Wanninger. He's a third-year PhD student at Northwestern University, and he's not on the job market yet, but in a couple of years, he's going to be interested in industry jobs, so look out. And Nick will be telling us about getting a handle on unmanaged memory.
Thank you. All right, so I want to start this talk out with kind of a motivating question, which we kind of tried to answer throughout our work here, which is whether or not we can move a heap object in an unmanaged language like C. You might ask why you want to do this, and I want to start out with a little bit of a story time to motivate this. So I want this story to focus on a little tool, which I think we all know. It's our favorite recently corporatized and rebranded tool, Redis. It's a very popular key value store written in C. It's often used as some kind of cache in front of a more complicated database. And usually there's like an LRU policy where you evict keys over time. And because of this, on long-running instances, fragmentation can run rampant. And what this looks like is when Redis allocates its keys on a heap and then decides, oh, I want to evict some of these keys because I want to put new keys in the database. It then frees those keys, and now there's a bunch of holes on the heap that are wasted memory, fragmentation, if you want to call it that. And we all know what wasted memory means. It's one of two things, usually one caused by the other. You pay for more memory on Amazon, and then your boss gets mad at you for paying for more Amazon money. And nobody likes that. And so if you go online and you look up Redis memory usage, you get hundreds of posts like this on Stack Exchange. And in this example, this poor guy is he's got his Redis is using 60 times as much memory as it needs to overnight, because overnight their users log off and the sessions are freed. So it'd be really nice if we could take that heap with all the holes in it and turn it into a heap that looks like this, where we have all of our free memory on one side of the heap, and then we could return that to the OS or return it to Amazon if we wanted, pay for less, and save our quarter three revenue. So Redis actually attacked this themselves. So this was such a big problem that there was a big work, I think, in Redis 3 maybe, called active defrag. This active defrag is this ad hoc solution to solve this problem. And without going into it right now, active defrag is able to, in this particular plot, you can see memory usage grows over time. And then in the baseline in purple, it's kind of stuck at 125 gigs. But active defrag is able to move the objects and the keys around in memory to reduce the memory usage over time, which in this particular workload saves about 60 gigabytes, and your boss can be less angry. So back to that original question, it seems like we can move objects in C. I mean, Redis did. Unfortunately, active defrag is extremely specialized. This tool, I mean, I just have a subset of the code here. It has hard codes defrag routines for every single data structure in Redis. It's tied into the event loop. It pauses the threads. It's very integral to the system. And if you want to add a new data structure, you have to go in and worry about how active defrag will handle it. So back to that original question on whether or not we can move objects in unmanaged languages, we can do that, but I want to augment this a little bit with the word transparently. I think it would be really nice to be able to do what active defrag does, but just not with no additional programmer effort. So unfortunately, this is generally pretty hard. Moving heap objects in these languages is pretty difficult because of pointers. To move an object, the runtime would need to find all of the pointers to an object and then update them to the new location of that object. And unfortunately, like a runtime or an allocator, all that it sees is a big array of bits on the heap, or not even on the heap, on the stack maybe, and it's all untyped. And so if you were to just go through and find all the bit patterns which look like the pointer you're interested in and update them, you're going to crash your code. You're going to cause incorrect results. There's a reason like the BOEM GC is conservative in this way. So in this work, we focus on handles as a way to move these objects because moving memory with handles is actually trivial. Handles are effectively a replacement for heap pointers, and they coexist with pointers in the application. They are effectively a level of indirection, where ASPLOS everything is an abstraction. It's effectively a level of indirection through a handle table, where the handle table points to some heap entry. And if you want to move that heap entry, all you do is rewrite that table entry, and then the object is in a new location. So in the past, handles were used back in like systems before virtual memory, entirely manually. If you've ever written Pascal for a Mac, this is terrifying. And the reason that it's terrifying is because you have to manually translate the objects. And for the duration of the translation, it can't be moved because the raw pointer is in memory. And so you also have to worry about an additional lifetime. And that's just the source of all the bugs in the world, I think. So in this work, we enable unmodified applications to use these handles entirely automatically with no changes. And this gives you things like active defrag for free. And the way we do this is we have a compiler called Alaska, which takes your code at the LLVMIR level. I'm showing it in C here because it's less terrifying. And it automatically transitions it to use handles with no changes. And so for an example here, we took Redis entirely unmodified, we just git cloned it and swapped out the compiler. And we were able to, in blue here, defragment the heap with no changes, running. We just swap out the allocator and use handles. So that's all with no code changes, and we save on the order of the same memory as active defrag. And so this system we have is broken up into two components. I'm going to focus on the compiler here for time, but there's a little bit of runtime stuff at the end. So the compiler's main job is to automatically insert these translations. And before any access to a pointer, we have to guarantee that we check whether or not we need to translate a pointer or not. And we insert this call to Alaska translate, which gets inlined in the back end. And this function checks if X is a handle or not, and then translates it. So really quick, we'll go over what handles look like in this system, how translation happens. If you're familiar with virtual memory, it's very, very similar to page translations. In our system, handles are just specially encoded pointers, which means they coexist with pointers. So the stack is pointers, the heap is handles. So we have to check whether or not the top bit is set, which is just what we chose. Then we use this handle ID part of the handle to offset into the table, a lot like virtual memory in the page table. And then we apply some offset to that, and then we can finally get the pointer out. And so all of this is a bunch of extra instructions potentially, and in our system, it's about 5-6 instructions. And so where you place these translations matters quite a bit. So if you were to place the translation here inside of this loop, you're going to get some N translations, and you're going to be paying that translation cost all the time. And if you hoist it outside of the loop, you only get the one translation, but you have to, like I said before, while the translation is active, you can't move that object. And so the placement of these translations also imply a placement of these pins. And so what I'll do is really quick, kind of motivating this concretely. Let's say you have a handle X here, which points off in a handle table. You perform the translation, which gives you a pointer directly to the heap. Let's say then the runtime in between this line of code and the while loop decides it wants to move that handle to this new location. Well, now PX is an invalid pointer to an invalid location in the heap. And then this is probably going to crash your program. Maybe. That's the worst part. So while an object is translated, it can't be moved. And so the compiler basically uses pretty simple liveness analysis on the translation itself to place these pins either at like an optimal location. And we have a lot of techniques. All of this is very similar to read and write barriers in garbage collection. We can elide a lot of these in the real world, which saves us a lot of performance. But so what this gives us is a bit of a trade-off, right? While on the left, we have short lifetimes. You get some more mobility because less objects are pinned potentially, but you also will have more overhead because you're translating more often and you're pinning more often. On the right, we have long lifetimes with less mobility potentially. That's not actually a problem in the real world, but we also get considerably less overhead. And for time, I won't actually go into that delta, but so we took Redis and YCSB here and threw it at Redis and memcache D, throw them to YCSB, and sorry, those are gray up there, but the end-to-end latency impact of this is about 16%, and the 99th percentile is like the tail latency is only like 23%. So in the common case, it's not terrible. We actually see a lot of noise in this data because it's over like we tried to reduce it over the local network, but yeah. So this in really large applications with no code changes, we can have decent performance impact despite the level of indirection, and we get this memory savings with no changes. And so, like many grad student projects, this is still pretty early. There's a lot of future opportunities to optimize this compiler. For example, we don't do any alias analysis. So if we add an alias analysis engine to the system, we would be able to elide that branch check in the translation. There's also some backend optimizations. LLVM really doesn't like the way we do pins. There's also some stuff in spec, for example, with like indirect functions that kind of hurt us. So I'll really quickly go into the runtime. So the runtime provides what we call a service interface. The application interfaces to the runtime entirely through the handle table, and the service, all that it does is manage the mapping between them. And it's free to do whatever it wants there. One service we have is what we call anchorage, which does the defragmentation. And this is like a 600 line of code bump allocator that it's built entirely with the knowledge that it can remove memory. So we don't really have any fancy policies. And this is the allocator that we can use to get this. And so we think that the service interface is general enough for more than just defrag. Object mobility is a really powerful tool, and the managed language people have enjoyed it for quite a long time. So like one example, I mean, this is something we're looking at right now. We want to be able to optimize the spatial locality of data structures in C. So tracking access patterns, like the relationships between different objects and laying them out so that they're spatially and temporally local. Doing memory swapping at the object granularity, so you can swap a bunch of objects out to disk or move all your cold objects to like non-volatile memory or something, or object level bounds checking. I mean, having a runtime function whenever you do a memory access is a pretty powerful ability. So quickly wrapping things up. Alaska is a generalized object mobility framework that lets you use handles in unmanaged language, which with no code changes. And it also has a generalized framework for adding new capabilities on top of object mobility. And with that, we'll end up at exactly 12 minutes.
All right, so we have time for some questions. Please state your name and affiliation. First question.
Vadim Zalio from Cambridge University. Impressive work. So how confident you can scale up to the existing code base? Because people doing all kind of strange stuff, like using lower bits of the pointer to store the data, type cloning.
Yeah, so that's a great question. We have a set of assumptions that we think are reasonable. You can do anything with the low bits of a pointer, but if you assume something like the pointers are only 48 bits, it's not going to work there. So our restrictions are pretty much the same as like pointer authentication codes, for example, on ARM.
And without that analysis, how confident that you're catching all the situations where the pointers are handled?
So we had some troubles with some of the spec benchmarks because they break a bunch of rules constantly. We had to change some of the compiler optimizations for that. Currently, we don't do that automatically, but that's, I think, just engineering at that point. But yeah.
Hi, I'm Utali from UT Austin. So if the memory allocation is very fine-grained, then it's not. If that workload does not cause some fragmentation, so it's gonna be automatic actually overhead, right?
Yes.
So is there any consideration that?
There's a reason I didn't really bring up like spec or anything here, because they don't get any benefit here because they malloc all at the start of the program, run some boring workloads, and then free everything at the end. And so there's no benefit for defragmentation in this. But I think in those applications you would benefit in other ways with object mobility. You could, the locality enhancement and all of that is.
I'm Matt from TM. I wanted to ask, you mentioned that the way you use pins, VM doesn't like that. So could you shortly tell us how you do pins and why VM is denying
I
that?
would show it. I just unplugged, but we actually use the garbage collector interface in LVM, the system they use to track routes. And there's some weird backend results we get from like actually doing that in part applications, because I think it was mostly designed for JITs.
What do you mean by widgets? I was like, what's the negative feedback?
So sometimes it's a lot of our overhead, sometimes it's not a lot of our overhead. We have a benchmark in Maas, which actually speeds up by using it, which is strange. But yeah, there's a lot of weird results coming out of that, but I think it's a case of optimizing the backend.
Thank you.
Yeah, I'm Peng from Meta. Just wondering, how is the soundness of the whole thing? Because you said you don't do alias analysis. Is it always safe to do these transformations?
So we conservatively assume that when you call translation, when you translate a pointer, we assume it might be a handle. So there's always a branch check in there. We eliminate that whenever we can. If we know it's on the stack, we eliminate it. But conservatively, we have a lot more checks. That's it.
All right, our next speaker is Brett Gutstein. He completed his PhD working on the CHERI project at the University of Cambridge, and he's now an independent researcher based in Los Angeles. Okay, thanks very much. So yes, this is Cornucopia Reloaded, load barriers for CHERI heap temporal safety. And before getting into the main kind of research contributions of this work, I need to introduce CHERI, which is the architectural technology that underlies it. CHERI is a protection model. It extends our existing architectures with the capability data type, where a capability is effectively a fat pointer. It doubles the size of an integer pointer on the architecture and also adds 1 bit of out-of-band tags. The doubling in size allows it to include metadata that govern how it can be used. So one important piece of capability metadata is the tag, which must be set in order for a capability to be able to access memory. The tag is also cleared on invalid manipulations. And so this gives us the property that capability pointers cannot be forged, or we have referential integrity. Another important piece of capability metadata is the bounds, which limit the memory that a capability can actually be used to access. And so bounds help to facilitate the property that capability pointers to a memory object cannot be used to access memory outside of that object. This is spatial safety. One other important CHERI-related concept to know for this work is that of pure capability compilation, which is a compilation mode in which all language level and sub-language level pointers are lowered to these CHERI capabilities. And so for the rest of this talk, we can assume everything I say is in the pure capability world. So the goal of this work is to give heap temporal safety for user space C and C++ programs using CHERI. In other words, to make use after reallocation vulnerabilities on the heap unexploitable. And so the question is, what's the best way to approach this? Well, there's a couple observations to make. One is that explicit freeing in C and C++ mean that we can perform pointer invalidation as opposed to other techniques for heap temporal safety, like garbage collection or key lock checks. And pointer invalidation basically says that when a region of heap memory is free, we will invalidate all outstanding pointers to that region before it can be reallocated. And in that way, we'll avoid exploitable use after reallocation vulnerabilities. One nice thing about CHERI is that with pure capability compilation, every usable pointer is a valid capability. And so we can identify pointers precisely based on whether or not the capability's tag bit is set. Only capability size words with the tag bit set can be used to actually reference memory. And then another important observation about CHERI, though, is that it avoids additional indirection on capability-related memory accesses by design. And this is to work well in terms of performance with modern microarchitectures. So there isn't a single location that we can modify, like an entry in an indirection table, to achieve this goal that we have of invalidating all capabilities to a free region of memory. And so to get around this, we have to sweep all of memory to identify and invalidate all these capabilities. The naive approach is that when a region of heap memory is freed, we'll sweep all of memory and revoke or clear the tag of every capability pointing to it. This is sweeping capability location. This should set off alarm bells in your head, though. Clearly, from a performance perspective, this is not feasible.
But it is kind of the jumping off point for a series of projects that our group has undertaken to determine whether we can make this concept of sweeping capability revocation acceptable from a performance standpoint. And because we don't have too much time here, I think the easiest way to explain what's new about the Cornucopia Reloaded work will be to briefly talk about the previous projects we've done and how this work kind of builds upon them and improves. So the first work I'd like to introduce is called CHERI. It was presented at Micro 2019. And this was a feasibility study on x86 machines that improved upon this naive idea I mentioned before. The most kind of obvious optimization is to do batching. So instead of sweeping all of memory on every call to free, we can have a tunable quarantine buffer of memory that's been freed by the application but has not been given back to the allocator yet. And then we have a bitmap to indicate which regions the revocation sweep should actually be looking for in terms of revoking capabilities to them. Another optimization in CHERI was to introduce architecture-supported capability dirty tracking, kind of analogous to dirty bit tracking that you may be familiar with in page table entries. And so basically that allows the algorithm to skip pages that are known not to contain capabilities or to be cap clean, in other words. And then finally, they introduced a C-load tags instruction, which allows a cache line to be scanned for valid capabilities without loading the underlying data. So we can basically check cache lines for capabilities without actually polluting the cache if they don't contain any capabilities. So CHERI, in summary, kind of actually yielded some promising results for execution time overhead with this batching approach, but it was only in simulation. And it also required the application to be paused for the entire sweep, which is a total non-starter for any kind of interactive workloads. So the next bit of work is Cornucopia, which was presented at IEEE SP 2020. And in this work, we actually implemented a fully elaborated kernel subsystem to perform the sweeping capability revocation in CHERI BSD, which is our CHERI layer 4 free BSD. We modified user space allocators to use revocation, and we actually did evaluation on real CHERI machines. So this was on FPGA. This configuration was a dual core 50 megahertz CHERI MIPS system with single issue in order pipelines. Besides the evaluation novelty here, though, another thing we did was to actually start trying to make the sweep concurrent. So we made improvements by using the capability dirty tracking bits in the PTE that I mentioned before. We improved the algorithm to basically, a rough outline of it is the revoker can make a pass or multiple passes of an application's memory concurrently with execution. And then a final pass will run with the application paused. But the nice thing about this is it only has to examine pages that were observed to experience a capability store concurrently with the previous pass. So kind of the simple invariant in this world is any page to which the application stores a capability will be examined by the subsequent revocation pass. And theoretically, the final revocation pass will be shorter and won't actually have to look at all pages because not all of them will have experienced concurrent stores of capabilities. So in this work, in summary, we did manage to significantly reduce pause times relative to the naive world-stopped CHERI revoke baseline. And when sweeping in parallel, we also reduced execution time, which was nice. But pause times were still far too long for interactive workloads, which we'll see a little bit later in evaluation. And that basically leads us to Reloaded, finally, the work that we're actually talking about today. And the main novelty here is that we've introduced a new algorithm for sweeping capability revocation inspired by ideas from garbage collection literature. Whereas in the Cornucopia world, we are tracking capability stores. In Reloaded, we want to intercept capability loads, kind of similarly to like load barriers, the load barrier concept in garbage collection. So the brief sketch of this algorithm is we start a sweep by briefly pausing the application and then doing something, which I'll talk about later, to configure all capability loads from all pages to fault. We then start sweeping memory concurrently with the application execution, resuming the application, and we progressively allow capability loads from each page after it has been swept by the revoker. When the application attempts to load a capability from a page that hasn't been swept yet, it takes a fault, and the kernel revocation subsystem will sweep that page synchronously before allowing the load to proceed and succeed. And so the invariant here is that once your revocation sweep's been started, no register can load a valid capability until the page containing it has been swept by the revoker. And so any valid capability that ends up in a register is guaranteed not to be subject to revocation. And so we can store it anywhere and we don't need to care about it from that perspective. So in theory, this algorithm should offer much shorter pause times and less work done overall per sweep relative to Cornucopia. And another contribution of this work is that we evaluated it on the 2.5 gigahertz quad-core server class ARM Morello system on chip, which is a kind of server class chip produced by ARM, real silicon. It incorporates CHERI technology and also incorporated novel architecture features specifically to support this type of algorithm. And so diving into those architectural features a little bit, we designed what we call capability load generations, which kind of in a slightly abstract sense, we can think of as having one global control bit, which is GCLG for global capability load generation. And then each page table entry has an LCLG bit for local capability load generation. And the behavior of these bits is that when a PTE mapping experiences a capability load, if the LCLG value doesn't equal the system GCLG value, then the load will fault. And we kind of expect this to be used in the sense of, in a steady state, all PTEs have their LCLG equal to GCLG, and all capability loads proceed normally. But when we flip the global bit, all capability loads will start to fault. And then the fault handler can process them for revocation, flip the PTE bit LCLG, and then restart the load, allowing it to succeed. So how do we actually use these architectural features? Well, basically, I'll just kind of add some more color to the load side barrier algorithm that I mentioned before. So when a revocation sweep is initiated, there is a stop the world phase. It's very short. We flip the GCLG bit and do some other things like invalidating TLBs, sweeping the register file and places in the kernel where user space pointers might be held so that nothing can like escape revocation. And then we resume the application. The sweep proceeds concurrently. And again, yeah, once a page has been swept, we can flip the LCLG bit to allow loads to proceed. And any capability load faults that the application experiences will be handled synchronously, and the right thing will be done with DPT bits. So now jumping into a little bit of evaluation, the paper goes into much more depth. We don't have too much time here, so I'm just going to highlight a few key takeaways. Here we're looking at wall clock overhead, lower is better. And we have prior CHERI work, the ones that we introduced earlier in the talk, which we re-implemented and evaluated on Morello, as well as other published techniques for heap temporal safety that don't use CHERI. And those numbers are coming from their papers, so that's important to know. And here we're looking at normalized runtime overhead on some spec CPU 2006 benchmarks. Interestingly, I mean, most of the spec CPU 2006 benchmarks don't actually hammer the heap enough to make the differences between these approaches clear. But we can see on the right in Omnet and Zalink, the differences do show up. And we have on the left of each kind of bar cluster, reloaded is in blue, Cornucopia is in orange, and CHERI looks in green. We see that all three CHERI-related approaches compare favorably to other techniques like state-of-the-art techniques that don't use CHERI. And we also see what we expect, which is that CHERI-Vok's wall clock overhead is higher than the other two techniques, the CHERI techniques, because it can't be run in parallel, whereas Cornucopia and Reloaded can. And so when we run it in parallel, the wall clock overhead goes down. We also see nicely Reloaded seems to have slightly lower wall clock overhead relative to Cornucopia. Another takeaway for evaluation is actually looking at these pause times. This is kind of a busy chart, but it's a logarithmic scale box plot. And what we're measuring here is the amount of time spent in each phase of each revocation algorithm across some benchmarks. So just the highlights, one important observation, we have CHERI-Vok stop the world phase, which is the entire phase, the whole algorithm in blue. Cornucopia's concurrent phase in orange and Reloaded's concurrent phase in purple. For each benchmark, those are the same, roughly. And that makes sense because they're all doing the same thing, which is the sweep of all of memory. When we look at Cornucopia's stop the world phase, which is in green, we can see that it is significantly shorter than its concurrent phase, though the difference between them depends on the benchmark. And also it's still quite a lot of time. Even on a fast Morello board, we're looking at milliseconds here, which is not really suitable for interactive workloads. As a final observation, though, the Reloaded stop the world phase in red is roughly constant across benchmarks and orders of magnitude lower than the Cornucopia stop the world phase. It's which suggests that it might be suitable for these interactive workloads. And now, final graph we're looking at here is kind of narrowing in on interactive workloads. This is the PostgreSQL pgbench transaction workload, and we're looking at a QO distribution function of tail latency for transactions here. So we have a few designs under test. The blue line is just the benchmark running, no instrumentation. The orange line is the bookkeeping required for doing sweeping capability revocation, but no actual sweep. The green is Reloaded, red is Cornucopia, purple is CHERI-Vok. And the dashed lines you can see there are the median pause times for the corresponding algorithms. And basically the thing that jumps out here is that for Cornucopia and CHERI-Vok, you can actually see in the CDF transactions getting trapped behind these long pause times. That basically means they're not so good for these interactive workloads. But when you look at the relative line, not only is the tail latency CDF better, but the shape of it really closely matches the shape of the orange one, which has no sweep at all. It's just bookkeeping overhead. And so this suggests that not only is it better for tail latency, but it kind of matches interactive workloads better than the previous algorithms. So to wrap up, relative to Cornucopia, Reloaded features application pause times that are roughly constant across workloads and orders of magnitude shorter, and seem suitable for interactive workloads. And we didn't get into this in detail, but it doesn't incur additional walk clock or CPU time cost, and in fact comes with a slight reduction in DRAM traffic. And then in terms of related work, if you're interested in this kind of thing, as of fall 2023, Reloaded Allocation is released in CHERI BSD and enabled by default. And there's also the CHERI embedded platform presented at Micro 23 that adapted this algorithm to an NMUS embedded system and used architectural and microarchitectural integration to make it very efficient, which is cool. Thanks, and I'm happy to take questions.
We have time for one question, and also if the next speaker can already set up.
So my question is some sort of TLB revocation required for this, and whether the temporal protection that's like the latency of that, is there some kind of guarantee where you could batch them to reduce the TLB shoot down?
Yes, exactly. So in the slow time algorithm, basically the first thing we do after flipping the GTLG that I mentioned is to do TLB evaluations. And yes, because we batch, we are doing a significant amount of batching. So we're not paying that cost, for example, on every free call. It's significantly batched.
Cool, thank you.
All right, our next speaker is Zhang Zhu. He's a fifth-year PhD student at Cornell University, advised by Professor Cristina Delmitru. His research focused on improving the performance and efficiency of cloud computing systems. And he'll tell us about some work he did at Google.
Yeah, sure. Hello, everyone. I'm really honored to be here to present our work, calculating a memory allocator at warehouse scale. Data center tax is the cumulative time spent on common service building blocks of diverse data center applications. These building blocks include serialization, remote procedure calls, compression, hashing, data movement, and memory allocation. Optimizing the components of data center tax is a promising way to improve the efficiency and performance of the entire data center fleet, as all classes of applications can benefit from such optimizations. In this work, we focus on the memory allocator, which constitutes a substantial component of warehouse scale computation in Google's production fleet. Memory allocator directly affects the data locality of allocated objects. So optimizing the memory allocator does not only reduce the CPU cycle spent in the allocator itself, but it also provides significant opportunities to improve application performance. To this end, we have performed the first comprehensive calculation study of TC-malloc, the memory allocator used in Google's production fleet. We derived unique insights from our calculation study and use them to optimize TC-malloc for warehouse scale environments. We'll start with a brief introduction on TC-malloc system architecture. TC-malloc is a fast multi-threaded malloc implementation. Like most modern memory allocators, TC-malloc has a tiered cache structure. The front end consists of per CPU caches, which provide fast allocation and deallocation of memory objects to the application. The middle tiers are the transfer cache and the central flow list. They are responsible for refilling the front-end cache. Finally, the back-end page chip fetches and returns memory from the operating system. We first conduct a general calculation study to see how TC-malloc behaves in our production fleet. The right figure shows the relative amount of CPU cycles spent in the memory allocator over a 2-week period, where the malloc CPU overhead accounts for 4.3% fleet CPU cycles. For the top 5 applications with the highest malloc usage, the memory allocator makes up of 3.6% to 10.1% CPU cycles. For memory overhead, it takes to 22.2% of the total heap size of applications in the entire fleet. 18.8% overhead is called external fragmentation, which is an unused memory cached by the memory allocator. The remaining 3.4% overhead is internal fragmentation, which is a slack between the allocated size class and the requested object size. The rest of the general characterization studies are presented in the full paper, which includes allocation latency, CPU cycles, memory fragmentation breakdown, and distribution of allocated objects and their lifetimes. Next, we'll take an in-depth look at each tier in the TC-Malloc cache hierarchy to uncover performance insights and potential optimization opportunities. We start with the per CPU cache, which is the front-end cache that directly interacts with users' code and provides fast allocation and deallocation of memory to the application. A per CPU cache is shared by the software threads scheduled on to run a given CPU core. To avoid populating caches for all physical CPU IDs available on the platform, TC-Malloc uses virtual CPU IDs to index the per CPU caches based on the number of CPU actually used by the application. We notice that the dynamic nature of data center workloads can lead to disparity in front-end cache usage. The figure on the left shows the number of worker threads of a middle-tier service in our searching service stack. We can see that the number of worker threads constantly fluctuates. The figure on the right shows the average miss ratio over all per CPU caches. The x-axis refers to a virtual CPU ID, and the y-axis refers to the average miss ratios. For per CPU caches, we can see that for virtual CPU ID 0, it suffers the highest number of misses. And for per CPU caches with the higher virtual CPU IDs, they will only be taken into use when the number of concurrent worker threads grows high, so the miss ratio is substantially lower. This clearly demonstrates that higher index per CPU caches are infrequently used, and this disparity suggests a need for a heterogeneous cache design. To tackle with the dynamic loads, we propose heterogeneous per CPU caches that can be dynamically sized to balance the misses across all the populated caches. As shown in the right figure, we employ a background thread that periodically resizes and reallocates the capacity from lower utilized cache to higher utilized ones. We record the total number of misses encountered by each per CPU cache and use it as a proxy for cache utilization. By balancing the cache utilization, we can reduce the initial cache capacity of front-end cache without sacrificing application performance, which helps us reduce fragmentation and memory usage. The next component in TC-Malloc cache hierarchy is the transfer cache. When the per CPU cache is depleted or full, it reaches out to the transfer cache to request or return a batch of objects. The transfer cache provides a centralized repo of objects that is shared by all the per CPU caches. In this figure, we use this red circle to represent a memory object. As shown in the animation, the transfer cache allows memory objects to transfer between the per CPU caches. Although TC-Malloc itself is a user space memory allocator, it still needs to accommodate hardware cache topology to achieve the desired performance. Oh. Maybe the ones on the right. I'll give it a try. Hmm. Oh. Yeah, thanks. Thanks everyone. And although TC-Malloc itself is a user space memory allocator, it still needs to accommodate the hardware cache topology to achieve the desired performance. The left figure shows the core-to-core access latency on a production platform with multiple loss level cache domains. And we can see that the inter-cache domain access latency is 2 times of the intra-cache domain access latency. Warehouse scale applications often span across multiple cache domains. And as shown in the right figure, a centralized transfer cache can lead to situations where the memory objects are transferred between per CPU caches attached to different loss level cache domains. And we can suffer from increased data transfer overhead. To minimize inter-cache domain sharing, we design non-uniform cache access aware transfer cache that track an array of free objects local to each last level cache domain. As shown in the figure, each NUCA-aware transfer cache only serves allocation and deallocation requests originating from its own last level cache domain. This can improve the cache locality, reduce the last level cache load miss rate, and improve application performance. Finally, we have the central for list and the page heap. These two are the places where we make memory packing decisions. In the central for list, we pack objects into spans, and the page heap is the place where we pack spans into huge pages. Due to time limitation, I will focus on page heap in this presentation. TC-Malloc's huge page-aware page heap manages memory in huge page size chunks to take advantage of transparent huge page support in the kernel. By covering consecutive pages using huge pages in the page table, we can reduce stalls by increasing the TLB coverage and reduce TLB misses. Let's first take a look at the memory fragmentation breakdown in TC-Malloc, which is shown in the left figure. We can see that the page heap, which is a place where we pack spans into huge pages, is a major source of memory fragmentation. The figure on the right shows the memory organization of TC-Malloc. Objects of fixed size classes are packed into spans, and spans of various sizes are packed into huge pages. Since a huge page can only be fully released to the operating system when all its spans are free, now we'll take a closer look at when spans will become free. So the first thing we notice is that spans are not equally likely to become free. We perform a correlation study of span lifetime versus span capacity, which is the number of objects per span. We measure the return rates of spans with different capacities, and the result is shown in the figure. The x-axis is the span capacity, and the y-axis is the span return rate. The leftmost data point shows the spans allocating large size classes that can only hold one object. When the only object is returned, the span is released, resulting in a high span return rate. In contrast, spans with a significantly larger capacity are long-lived and have a much lower return rate. This indicates that we can use span capacity as a proxy for its lifetime to distinguish between short-lived and long-lived spans. So page heap is a place where we pack spans into huge pages. And if we do not take the disparity in span lifetime into consideration and simply pack short-lived spans and long-lived spans on the same huge page, this can prevent a huge page from being released, leading to increased fragmentation, or we will need to sub-release a huge page by breaking it into smaller pages, which reduce the huge page coverage and increase DTLB misses. To maximize the probability that a huge page becomes totally free, we propose to make the page heap lifetime aware. We use span capacity as a proxy for predicting span lifetime and pack long-lived spans and short-lived spans on separate sets of huge pages. This allows the lifetime-aware page heap to densely place short-lived allocations on dedicated huge pages and release memory to the operating system in complete huge pages. This can help us improve huge page coverage, reduce TLB misses, and boost application performance. We evaluate all our design choices with fleet-wide A/B experiments in our production warehouse-scale computers. Evaluation results show that by redesigning the memory allocator for warehouse-scale environments, we achieve a 1.4% improvement in throughput and 3.4% reduction in memory usage for the entire data center fleet. For the applications with the highest malloc usage, we have observed even higher improvements. At our scale, even a single % improvement can translate to significant savings in real server cost. For the conclusion, we have performed the first comprehensive characterization study of TC-Malloc, the memory allocator used in Google's production fleet. We derive unique insights from our characterization studies and show that a memory allocator using warehouse-scale computers need to adapt to the dynamic resource usage of warehouse-scale applications, be aware of the heterogeneity in hardware platforms, and utilize diverse lifetime information to make memory packing decisions. Based on these insights, we designed TC-Malloc for warehouse-scale environments. Evaluation results show that we have achieved a significant improvement in fleet productivity. And thank you, and that's the end of my talk, and I'm open to any questions.
All right, we have time for some questions.
Thanks for the fantastic talk. I'm Deep from Zoox. I have a question. In order to get the instrumentation required from TC-Malloc, was there any overhead that increase the latency of the application that you were running? Or these are just zero overhead insights?
Yeah, most of those optimizations improve node performance degradation and simply improve the throughput and reduce the memory usage.
God, I'm not talking the optimizations. I'm talking about like in order to understand the per thread, in order to enforce the policy, you need some insights from how much is the buffer per thread that is being used, right? Or how many thread? What is the input that you're using to enforce the policy?
Google's production workloads.
And what's the telemetry information that you're using?
We're collecting like the throughput of each application, and we're also collecting the memory usage and the fragmented memory in each application.
Okay, got it. So nothing, you didn't have to modify tcmalloc to get anything, right?
Yeah, we need to modify the tcmalloc and roll it out to the entire fleet. So all the applications using a memory allocator will use the new version of tcmalloc. And it's an A test with optimization and without the optimization.
Got it.
Yeah.
Okay, thanks.
No problem.
Any more questions? In that case, I'll ask one. Okay, so you've worked on systems in academia. You've worked on warehouse scale systems. How do you think the insights from fleet-wide deployment in this case can carry over and can be exploited in academic work?
So although in this work we are focusing on the tcmalloc, the memory allocator used by Google, but since most of the memory allocator or most of the modern memory allocator, whether it's gmalloc or MAMalloc, they share a system, they share a similar like tiered cache structure, and they're also packing memory objects at different granularities. So the insights we have learned and the optimizations we have can be applied to other memory allocators that are used for data center workloads. That's what I'm thinking.
Thank you.
Yeah. Thank you.
Any more questions?
Yeah.
If not, let's thank the speaker once again. So our next speaker is Professor Zhangshao Chu, who's a assistant professor at City University of Hong Kong. Prior to joining the City University of Hong Kong, he was a tenure-track assistant professor at Michigan Tech. He got his PhD degree from UC Riverside.
Words. Okay. Yeah, thanks for the introduction. I'm Jun Chao, and in fact, because my students cannot get the visa, I'm going to present the paper today. Today I'm going to talk about my work about the GC swap code design to enable the more apps, faster hot launch on mobile devices. This is a kind of joint work among multiple universities. As we know that mobile devices and mobile apps has become, a crucial part of daily life for everyone nowadays. In the past decades, the increasing of mobile apps market values and the number of downloading are significant. As there are more and more apps, the mobile users often switch, among the apps. Android typically has one launch apps in the foreground, which allows the interaction with the users. So the app launch performance is a very important metric of the user experience. There are two ways to launch apps: the cold launch and the hot launch. As shown here, the cold launch refers to the apps starting with a new process creation, which means the app launch from the scratch. To enhance the app launch performance, Android cache the apps in the background when there is sufficient memory. Then we can have the hot launch where app launch from the background cache stays. It has much better performance than the cold launch. We test on multiple apps and observe that the cold launch time is about 8.75 times longer than the hot launch time. So we want a larger capacity of capturing apps in the background to enable more hot launch and less cold launch. And this can getting better. This can ensure that we can get better user experience. To increase the app's caching capacity, there has been two directions. The first is enabling the swap provided by the Linux kernel to cache more apps. When the memory pressure becomes high, the swap mechanism uploads the least recently used pages to the swap partition. However, this LRU-based swap scheme in that is designed for the general workloads from the Linux perspective and neglects the specific characteristic of Android. So our study shows that there are two issues using the swap schemes for Android apps. First, the GC may offset the effects of swapping in terms of the caching more apps. For example, in the upper right of the upper right providing results, when the GC is triggered at around 37 seconds, there's a spike in access objects due to the chasing work of GC. Even though they are not necessarily used by the app mutator threads. So we have a high memory pressures here. Another issue in that is the hot launch process may be delayed because the necessary pages could be swapped out. For the same example, during the hot launch stage at around 53 seconds, the app needs to access many objects that have been swapped out. So the hot launch process in that it is blocked. To address these issues that the pages swap out would be swapped back due to the chasing GC, and to cache more apps. The second method in that is to use a bookmarking GC, such as Marvin introduced in the ATC20. It saves the corresponding references for each swap out object and locates the live objects based on the references without touching and swapping back this kind of objects. So despite its ability to cache more apps, Marvin still fails to achieve the desired hot launch performance. This is due to the three drawbacks of Marvin. The first is it requires a long stop-the-work pause time to maintain the consistency between the separated references, information, and the objects. And the second limitation in that is the Marvin swaps objects at page granularity and has low swap efficiency. And the third issue in that is the Marvin employs a kind of on-demand swapping during the hot launch process. So in some, neither of these two methods in that can enable more apps cache in the background at the same time, having efficient hot launch. So the goal of our paper is to maintain or even improve the hot launch performance while caching more apps simultaneously. So to achieve our goal, we first examine the distinct states of objects before and after switching an apps to the background. We can categorize all objects into two types: the foreground objects and the background objects. The foreground are those allocated when the owner apps is in the foreground state, and the latter one in that are those allocated when the owner apps is in the background state. So at the moment that an app switches to the background, all existing objects are considered as the foreground objects, and all newly allocated objects are the after the switching are classified as the background objects. So then to figure out the nature of the Android launch procedure, we identified two special types of foreground objects that tends to be reaccessed during the next hot launch. The first one is the near root objects, and second one is the foreground young objects. So by investigating the usage pattern of apps, we make two key observations. The first, by measure the lifetime, which means the GC count of the foreground and the background objects. When the owner apps is in the background, we find out that the foreground object in fact occupy a large memory footprint and have a longer lifetime compared to the background objects. And second, after conducting the experiments to analyze the object reaccess during the hot launch, we can observe that the near root objects and the foreground young objects, they occupy a large proportion of object reaccess during the hot launch process. So built upon these two observations, we developed a cross-layer memory management framework, and contains two major components. The first one is the background object GC, and the second one is the runtime guided swap. The background object GC limits the chasing range of GC to the background objects only, avoiding touching long runtime foreground objects. And the runtime guided swap identifies objects that will be accessed during the next hot launch by utilizing the runtime information and guides the swap mechanism in the Linux kernel. So more specifically for the background object GC, we use it to replace the existing major GC in the ART when the apps is in the background. It aims to free the garbage objects only from the background objects to minimize access to the foreground objects. It first provides the object separations by adding a region type flag to the metadata of the regions, indicating whether these regions contains the foreground object and all the background objects. To conduct liveness analysis for background objects, we propose the use of an additional table to record or modify foreground objects. Then our GCs ship instruction with the caption values to translate between the foreground objects, address, and the offset of the corresponding byte in the color table. Once objects that are separated into different regions, the GC initializer is color table to empty, and when the apps run in the background. The multiple objects are recorded in the color table, and then when the GC starts, it frees garbage objects in the background objects while minimizing the access to the foreground foreground objects. Because of time limitation here, for more details you can refer to our paper. Then as for the second component, the runtime guided swap, it consists of two steps: the object grouping and the page swapping. The object grouping is a full GC process that classify objects based on the runtime information and access pattern of objects, and then groups them into pages. Here, besides the near root objects and the foreground young objects I just mentioned, we also need to identify working set objects which are currently being used by the apps. The working set objects, they ensure the necessary objects are required by the apps to run in the background, and they're not selected to be swapped out. When providing the object grouping, unlike existing the BFS-based GC in Android, we utilize a kind of BFS algorithm with the first in, first out mark queue. And similar to the existing concurrent GC, we enable the root barrier mechanism during the BFS traversal. So running concurrently with the chasing and the mark procedures of the GC thread, the mutated thread also performs the mark operation through the root barrier when they access an object. So finally, we can classify objects into different categories. And based on the object classification, we have the copy operation selects the corresponding types of region as the destination to region for every mark object. Here we have three regions: the launch regions, the working set region, and the code region. In the second step, based on the object grouping procedure, all foreground objects, they are grouped into three types of pages. Then we can make a new modified memory advice system call in the Linux kernel with the call runtime option, so that we can optimize the swap out mechanism by swap out the code regions only when an app switch to the background. And while the app is in the background, we will periodically execute the memory advice system call with the hot runtime option. It can find out the corresponding physical pages for those hot regions and move these pages to a highly used position in the LRU queue in this Linux kernel. As a result, this kind of hot launch pages are likely to be swapped out and ensure the fast hot launch performance. So we evaluate Fleet on a Google Pixel 3 smartphone and compares with the default Android and Marvin. We utilize two types of apps for evaluation. The first one are those manually created apps downloaded from the Marvin project. They contain small objects apps and where all allocated objects are 512 bytes, and the large object apps where all the objects in that they are 2K bytes. We also test on the most popular commercialized apps from the Google Play Store. As for the caching capacity, we can observe that the fleet can cache 1.3 times numbers of apps than the Android, the both large and small object apps. For the small object apps, the fleet can outperform Maven by 2 times in terms of the maximum caching and achieves a comparable caching capacity in large object apps. As for the commercialized apps, Fleet's maximum apps caching capacity is 17, which is 1.2 times than that of the Android with Swarm. Here in this test, we sequentially launch these apps in a round-robin sequences from Twitter to Candy Crush, as indicated on the x-axis. We use each app for 30 seconds and record the number of active apps cached in the background. Then to access how Fleet improves the caching capacity by reducing the working set of background GC, we measure the working set of GC threads when an app is in the background. We measure the number of objects accessed by the GC during the single GC execution and find out that on average, Fleet's reduction is around 7 times of Android. To access Fleet's hot launch performance, we test the commercialized apps under pressures with about 10 background max, and our result shows that the Fleet achieves faster average and tail hot launch time than Maven and Android for most apps. So specifically, the average speed up of the median hot launch time of Fleet is 1.6 times compared to Android and 2.6 times compared to Maven. And the 90% tail hot launch time of Fleet is 2.5 times and 4.4 times compared to Android and Maven respectively. The evaluation result also shows that here there's a kind of positive correlation between the speed up achieved by Fleet and the Java Heap percentage of apps. We also use the jank ratio and the FPS to present the impact of Fleet on the user experience. Compared to Android, Fleet shows a nearly identical average jank ratio and FPS, and compared to Maven, the Fleet demonstrates that at around 20% improvement in the jank ratio and FPS. So here is the here's the summary of our work and the presentation. For more details, please refer to our paper. Thanks.
We have time for one question, and the last speaker can already set up. If not, I'll ask one. So I'm really intrigued by this idea of co-designing garbage collection with the operating system layer. Do you think there are other problems than cold start where that kind of pattern applies?
Oh, I think that's a very good question. So in fact, recently we find that to further improve the performance, in fact, we need to further refine the GC. For example, because we found that the GC anyway have to change the objects, right? Mm-hmm. So and anyway we have to we might be like for example the ring rendering and in fact affect the user experience. So we think about how to improve the GC by maybe using the tracing based GC and the reference counting.
Okay,
thanks.
Thank the speaker once again. And so the last talk of the session is by Michael Moffett. Michael has been a software engineer at Google for nearly 10 years and currently serves on the TPU performance team. Previously, he worked at IBM Research on problems relating to physical synthesis and hardware-accelerated functional verification.
Great, thank you, Martin. And by the way, there's a few chairs out there if people standing want to sit down. I see about 4 or 5 over there, so feel free. So let's start out with the obvious. Machine learning has been on a tear. Hopefully, most of you were in the audience for the keynote yesterday by Amin Vedat, who is one of our chief thought leaders at Google. And as he spoke about at length, every chart that you can find in this space is an exponential graph. This is one of my favorite visuals. This was actually just published last Friday. It's probably already out of date. But of course, this Cambrian explosion in model architectures would not be possible if not for the corresponding evolution in machine architectures, whether it be TPUs like the ones you see here from Google or GPUs. Just a couple of weeks ago, I think Meta announced the 5-nanometer version of their MTIA chip. So this is a really exciting time to be alive. And of course, it's worth noting that the performance of these devices is only as good as the programs that you feed them. And so it's no accident that we see the emergence of new software stacks that are responsible for mapping the elements of the ML models onto the resources of the accelerator. For any of you that have an interest at the intersection of systems and optimization, this is a playground. You can throw a dart at this slide and find an NP hard problem worth solving. And one of the more interesting and elegant topics is that of static memory allocation. And what makes this such an attractive problem is that it is not done downstream at execution time, but rather upstream and offline. And that may seem a subtle difference, but there are two huge implications. One of them is that there is enormous flexibility. So you see here the lifespan of an ML model. So the x-axis is time, and each block is a buffer. And if you wanted to add one more buffer and it doesn't fit, you can literally rearrange anything that you like, not in the horizontal dimension because that's time, but in the vertical dimension, which is the address space, you can move blocks around. The downside of that flexibility is that the space of possible assignments is staggering. Now, before I get into detail about how we solve this, I have to delve into the related problem of rectangle packing, because this is a variant of rectangle packing, which has been studied for decades. And there's a couple of different approaches that you can take to solve this problem. One is to model it as a constraint satisfaction problem, where the variables are the rectangle locations, and the values are the different coordinates that you can assign to them. Right, so the depth of the search tree is n. The branching factor is the number of unique spots in this grid, and throughout that search, you can check the consistency of the solution by looking for overlaps between rectangles. But there's a second way of formulating this problem, which is called the meta CSP. And in the meta CSP, you have a variable not for every rectangle, but for every pair of rectangles. So for rectangles 1 and 2, 1 and 3, and the values that those variables can take on are each of the 4 possible pairwise relationships. So above, below, left to right. So the depth of this search tree is roughly n squared over 2. The branching factor is 4. And you can check the consistency by converting the pairwise relationships into the edges of a directed acyclic graph and checking for negative cycles. Don't worry about it. It doesn't matter for this talk. Just trust me that there's a way of checking the consistency in an easy way. What's nice about the search space is that it's independent of the grid size. So whether your rectangles are 1 by 1 or a million by a million, it has no effect on the runtime of the algorithm. So back to static memory allocation. If you haven't read this paper from last year's ASPLOS, I think that you should, because believe it or not, there's a third search space. And the idea here is that since we're only assigning the vertical offset values, we can imagine dropping these buffers one at a time to the bottom of the space. So imagine I drop buffers 1, 2, 3, or 1, 3, 2, right? And you can backtrack whenever you encounter an infeasible solution. And so what the authors do here is they come up with several very nice domain-specific heuristics, and they rig it up to a constraint solver and then backtrack whenever the problem seems to be infeasible, and turns out to be much faster than other systematic approaches. So the tele-CSP, it's really cool. It has a couple of drawbacks that I thought I would briefly highlight here. So I have an allocation here. It's got 5 buffers. And if I asked you to come up with the tele-CSP solution for this instance, you might come up with a solution. So the way to read this is replace buffer 5 at offset 0, buffer 3 at offset 4, and so on, ending with buffers 2 and 4. Now, you could also swap those last 2 because the order of those doesn't matter. So you could go 5, 3, 1, 4, 2 instead. By my count, there are 8 different ways that you can enumerate the possible solutions for the same allocation. Now, is that a problem? The answer is maybe. If you get lucky and you encounter one of these early on, it might not make much of a difference. But generally, in recursive depth first search, you want to reduce the search space as much as possible. So that's one issue. The second issue, so here's another allocation, and I put buffer 1 and then buffer 5. This is a legal allocation. Nothing is overlapping. Nothing is going beyond the memory limit. But when I go to place another buffer, I run out of space. And this is one of the limitations of the binary constraints in the SAT-based encoding. It can't capture the fact that we're going to run out of real estate at the end of this solution. By the way, in the vast majority of industrial benchmarks, this is the common case. You're cramming memory with as many buffers as possible. It's very hard to squeeze into any one. And so this is what most of the problems end up looking like. It's like a pigeonhole problem. And so this is a second issue with solving problems via the tele-CSP. Okay, so our approach has nothing to do with heuristics. Our overarching theme is to reduce the search space as much as possible. We've got 3 techniques. There's actually a 4th technique that's kind of buried in the paper. If there's time for the end, I can talk about it. the first thing that I'll mention is that, I noted this redundancy in the solution representation. It's not limited to the leaf nodes in search. So for example, I've got two nodes here that are in bold. Both of these turn out to correspond to the exact same partial allocation, right? So what we'd like to do, if possible, is to take the search space and to condense it or squeeze it as much as possible so that we'll only have one search node for every unique allocation. I'm not going to tell you how much time I spent making this graphic. This was not easy to do. All right, so let's take a look at this. So this is called a lattice, and what's different about a lattice is that there's one node for every unique allocation. So rather than storing the permutations, I have one node for every set of values that I assign. And so the question is, how do we transform the TLCSP search space so that we only explore the search lattice? The paper uses lots of math and terminology like offset monotonic and index monotonic, but I've got this nice big screen, so I'll just show you pictures. So there's basically two rules. Rule number one, always place lower blocks before blocks that are higher. So here's an example. I place buffer A, then buffer B, and then buffer C. But the thing about that last one is that there's nothing stopping me from going A, C, B, right? I could have put them in that order instead. And so we would say that this sequence is not allowed. It's a legal allocation, but the sequence is one that could have been reached a different way. And the other rule is that for blocks that are at the exact same offset, they have to be placed left to right. So again, we have buffer A, placed after that is buffer B and then buffer C. But you see that C goes in the middle. Nothing stopped us from going A, C, B instead. So because of this rule, we would eliminate that one. So both of these sequences, we would say, are not allowed in this new augmented search space. So here's the search lattice revisited. I've drawn some of these dashes. So if you see a dotted dash, I think that's a non-offset monotonic solution. If you see a dotted edge, it's a non-index monotonic solution. And so the nice thing about this is that every node has a single parent, and there's only one way of searching this tree that gets you to that terminal node, which is really nice. We can prune all these other assignments. Here's another one. I mentioned to you earlier that the length of this allocation is 21 units, but that length doesn't really matter. That could be 21 million. What really matters are these points where buffers are either being evicted or entering memory, right? So those are the points. And in between those, we have these areas that we call cross sections. Now, you can talk about feasibility within a cross section in a couple of different ways. One is just by taking the area of all the buffers in that cross section and adding them up. And clearly, if the area of those buffers is more than the memory, that cross section cannot be feasibly allocated. That's pretty obvious. The other is if you have a buffer that you've allocated and the height of that buffer is beyond the memory limit, that also is an invalid solution. Both of these, I think, are pretty straightforward. What you can do, though, is combine those into a much stronger lower bound. And the idea here is that for any allocated buffer, the highest one in any cross section, you can add on top of it the total area of the unallocated buffers. And if any of the cross sections eclipse that upper limit on memory, you can backtrack. And so this is a much more powerful way of doing inference than using pure binary SAT-based constraints. Last but not least, I'm showing you here a partial allocation that's been extended at least 3 different ways. So we have A, and then we can either place B, C, or D. And my claim is that regardless of whatever other buffers might exist in this problem, one of these 3 you can prune immediately right off the bat. And I'll give you a hint. If you see there's a little gap there in that third solution, right? These are offset monotonic solutions, so they have to be constructed from the ground up. So I can't place buffer C anymore in that spot. Even if I could have done so, that same solution will be explored through this other path, right? So we'd say that that third solution is dominated. And so what's the trick? It's a very simple rule. Never place a buffer above the minimum viable height of any unallocated buffer, okay? Okay, let's talk about results. The original algorithm was surveyed on 11 different benchmarks. We're going to show you a couple different things. First of all, I rigged up the CSP and Meta CSP solvers so that we can use them for static memory allocation. They both do terribly. Actually, the CSP doesn't solve any of them. The CSP solves all but 3. But mixed ILP beats all of them quite easily. And then we have telemalloc. By the way, it's worth noting, beating a mixed ILP solver in the year 2024 is very difficult. These ILP solvers are engineered very well. And so this is a pretty astonishing improvement. With mini-malloc, the improvement is actually even further. So I think the average improvement over telemalloc is something like 30x. It's about 300x over the mixed ILP. Of course, these are just 11 problems. I think they span actually quite a few different kinds of models like image and language and ResNet. But it's just 11. So we looked at a broader set of benchmarks, I think about 1,000. And here what we're showing is the number of milliseconds it takes to solve, and then the number of problems or the percent of problems that you can solve at that time. And so if you look at just the 1 millisecond, that's the leftmost part of this plot. You go from 15% of problems solved with mixed LP to something like 35, I think, with telemalloc, to like 85% with mini-malloc. And so it's a pretty substantial improvement if you look at actually any threshold on this graph. Last but not least, as a former academic, I'm sympathetic to the fact that only Google has these benchmarks, so none of you could really do these experiments. And so I put these results on the synthetic suite. For a couple of reasons. One is that I want to normalize the process of using synthetic benchmarks. I think it's fine. I think a lot of reviewers will ding you if you do this, but I think in some cases it's warranted. And also with these synthetic problems, you can tune the knob and make them more difficult or less difficult. And so over this synthetic suite, you have the number of buffers going from left to right. We see that going from the mixed LP to the telemalloc system is a pretty big improvement. The left graph is the average runtime or the median runtime, and the right is how many problems you can solve with the respective allocator. With mini-malloc, consistently is 1 millisecond for all of these. Can solve all of the benchmarks, no problem. So the question is, is there anything that the mini-malloc can't do? And the answer is yes, there are some. But here's one from a new benchmark suite that also has 11 instances, but they're really difficult memory allocation instances. And this instance is one of many that I think no allocator on the planet could solve in under an hour, except for mini-malloc. Mini-malloc takes less than a second for this benchmark. This is one of 11. I think I said not only are these benchmarks open, but so is mini-malloc. I checked this morning. I think it had 86 stars. Those are rookie numbers. So I'll tell you what, lunch is waiting for you outside. I have a QR code here. The more stars that this gets, the faster I'll answer your questions. So, does that sound good? That's all I've got. Thank you very much.
Right. Any questions?
Hi, I wonder like how, so it seems like so far the result looks extremely good, right? Like it's just solved within like a second. Have you tried to kind of like stress test it on like what is the biggest problem you can solve? Like, can you scale this to like very large ML model, including like training workloads?
Yeah, that's a great question. The answer is for the vast majority of real industrial benchmarks, it works just fine. With that synthetic generator, you can make the benchmarks as big as you want, and there is a point where eventually it chokes, and it takes minutes, if not hours. But so far in practice, those are few and far between. The vast majority can. The one thing I will mention is that this is implemented as an actual recursive depth for a search. And if you've got tens of thousands of buffers, eventually you blow through the stack. So I should probably re-implement it using a stack-based approach. And so there is that limitation, but algorithmically, I think this approach should scale pretty well for the vast majority of models. But excellent question. Thank you.
Yeah, so maybe I missed the story. Like, what's so unique about this one that the relationship of this allocator to hardware accelerated machine learning?
Oh, so yeah, a great question. So what this is doing, it's allocating instances that are eventually going to be run on a hardware accelerator. And the key difference in this algorithm versus all the others is just the fact that it is trying to exploit properties of the geometric structure to reduce the search space. So, I think I talked about mixed LP and CPSAT. Those are sort of geometric agnostic. They don't realize that there's this geometry involved. What mini-malloc is doing is it's finding these properties of these rectangles, whether it be the cross sections or the dominants, and it's exploiting those in its search tree so that it prunes much earlier than otherwise possible. And by the way, I think this allocator, I don't know much about PyTorch or the stack and meta, but I'm sure that there's a way that you could probably crowbar this into into that stack so that it solves those allocation problems more efficiently. So you'll have to let me know if you do that.
Right, any more questions? Let's thank the speaker once again. And this concludes our session. Thank you so much once again for all the speakers, 5 fantastic talks, and enjoy lunch.